So good morning all of you. Welcome to the second lecture on gravitation. You should remember that this is the first physical force and a fundamental physical force that you are studying in your course. So far, whatever you have studied was essentially modeling, whether it is collision or friction or any other force. But here we are discussing a force whose physical origin is known, coming from the masses. And as a preliminary to that, what I did was to briefly revise the basic concepts of dynamics. So the basic concepts are summarized in the three laws of motion formulated by Newton. So if I am to repeat them, the first law essentially defines an inertial frame of reference, assuming that you know whether force is acting on a body or not. So it says that if a body is not acted upon by any force, then there are special frames of reference where the body will move with uniform motion. It will not have any acceleration. The second law quantifies force, and the quantification, the way you express it mathematically, is done in the inertial frame of reference. And much later you will study that when you go to non-inertial frames like a rotating frame or a uniformly accelerating frame, there will be unphysical forces where Newton's law will have to be modified, the second law. So the second law essentially states that in an inertial frame, the acceleration, or even better, the rate of momentum change suffered by the body is proportional to the applied force. The most important thing here is that it is understood that applied force is known. We do not try to determine what the applied force is by looking at the acceleration. It is assumed that the applied force is known, and as I told you, for example, in the case of simple harmonic motion, we write F is equal to minus kx. That is what we write. In the case of electrostatic interaction, we write F is equal to E squared over R squared R hat. That is what we write. Or even better, we write E1 E2 by R squared R hat. And probably you may like to put a factor 1 over 4 pi epsilon naught, etc. So basically, what we are saying is that when I am speaking of the applied force, what I am doing is to model it based on a large number of observations and our own intuition, and then we plug it into the Newton's equation, dp by dt is F applied, and check whether our modeling is correct or not. This is something that we have to remember. The third law, as I told you, is essentially a statement of conservation of total momentum, which is a very, very fundamental principle. And we should do well to remember that, because later when I am going to work out problems involving gravitation, and later when others will teach you electrostatic interaction or even other forces, in many, many problems, conservation of momentum will be used extensively to find out what is the state of a particle after scattering, after collision, etc., etc. Conservation of momentum is but one of the conservation laws. So what I wish to do today is to state the other conservation law, which is very, very important for us, namely the conservation of energy. This is a very fundamental principle, and in physics, both conservation of momentum and conservation of energy have a very exalted place, very high position, and all theories that we propose should be consistent with them. However, at this point, we should add one statement of caution, or one statement that is of the nature of a clarification, and that is, whereas conservation of momentum is straightforward, conservation of energy is not a very straightforward concept, because energy can occur in many, many, many forms. In fact, the precise formulation of the law of conservation of energy involves thermodynamics, where you take it into account all kinds of energies and not necessarily mechanical energy. Whereas in your mechanics course, you are only going to deal with mechanical energy, but in thermodynamics or in any other discipline, including nutrition, you worry about how many calories you are consuming. That involves chemical energy, heat, etc., etc. It is that total energy that is conserved. So in that sense, a proper enunciation of the statement of conservation of energy really comes not from mechanics, dynamics that we learn here or in your higher studies, actually in the much broader area of thermodynamics. That is something that we have to remember. So now let me start with the statement of the conservation of energy. So the most important concept for us is that of the work done. And this is a technical definition. So what do I do when I look at the concept of the work done? What I am going to do is to assume that there is a certain force F, and this force is acting on a particle. So force acts on a particle, body, and the body moves. So let us say at time t equal to t initial time, the body was here. At a later time, the body is here. So this is t, and this is my, this is t1, this is t2, and let us imagine that there is a planar motion. This is my x coordinate and this is my y coordinate. So for intermediate times, let us imagine the body executed this motion. That is what we are looking at. Now what I can do is, at every point, I can find out what the displacement is. I can find out what the displacement is, and what I do is to evaluate the integral f dot ds, the component of the force along the direction of the displacement between t1 to t2 along this path. That is what I am going to do. You will study this at great depth in your higher classes, but essentially the statement is that if this is defined to be the work done, we say that a force is conservative if the work done is independent of the path. So let me repeat that. We say that a force is conservative if the work done is independent of the path. What does it mean? In particular, suppose a body started at a point, it went all around the place and came back because of the action of a force. Then irrespective of what this path is, the total work done is 0. Total work done is 0. So my force is acting in this direction, my displacement is in this direction, this is my F, this is my ds. So basically I sum over all possible things. If it is 0, then we say that such a force is a conservative force. It is important to remember that here work, the concept of work is a technical concept, and it is defined to be integral f dot ds. Now what does it mean? If you guarantee for me that the work done is indeed independent of the path, then again you will learn in your higher classes that this f can be written as, let us assume that it depends only on the distance, the derivative with respect to r of a potential. Derivative of a potential with respect to r, that is what we are going to write. So in doing this, I am assuming that the force depends only on the mutual separation. I will come to that later. So in which case, we get the condition that half mv squared plus v of r equal to constant. And this is the statement of conservation of energy. So, we identify half mv squared with kinetic energy, and this V of r is called the potential energy. So, if a particle starts with a certain kinetic energy, it will keep on decreasing because total energy is a conserved quantity until all its kinetic energy is converted into a potential energy. Or if a particle starts with a potential energy at rest, then it keeps moving in such a manner that the potential energy keeps decreasing and the kinetic energy keeps increasing. So, what is the example that we have in our mind? I take a body and throw it up with an initial velocity. It was all kinetic energy, but then when it reaches the topmost point, it is all potential energy. There its speed is equal to 0, the kinetic energy is 0, and when it starts falling down, there it was all potential energy, and when it reached back the surface of the earth or your hand, then it is all kinetic energy. So, that is what we have, and I am sure you people know that total energy is not a measurable quantity, only energy differences are measurable. Therefore, you can add any constant to V of r, it really does not matter. So, this is a preliminary that we should be familiar with. So, now I am going to state another conservation law. I am not going to give you any argument, but I will just state. So, I have demonstrated the conservation of momentum through the third law of motion. Of course, the third law of motion does not prove that momentum is conserved, it only states that momentum is a conserved quantity. I have also told you that there is a special class of forces called the conservative forces for which energy is conserved. By energy, I do not mean any energy, by that I mean kinetic energy plus potential energy, and that is all what matters to us in the course on gravitation. We do not have to worry about all other kinds of energy. And the third conservation law is the conservation of total angular momentum. At this point, it is not very useful for us to study how the conservation of total angular momentum comes from. Of course, we can make a statement that if the total torque is 0, then the angular momentum is conserved, but there are deeper issues. Let us not get into that. We will take that up, or whoever teaches you will take it up at the right time. Now, I told you that we are for the first time looking at a fundamental force. We are not simply modeling. So, let me recall what I told you in the last lecture. I say that there is friction, I say that there is viscosity, but friction is a very vague statement. For example, friction can be independent of the speed, the frictional force can be proportional to the speed, frictional force can be proportional to the square of the speed. All that we mean by friction is that it is always opposes the motion, and whatever energy you lose is dissipated as some heat or some such thing. The same thing happens in viscosity. So, it is a question of modeling. We do not ask for what the origin of the frictional force is. So, a good question that we can ask when we embark, when we begin on a study like gravitational field, is to ask, what are the forces which are the most fundamental from which every other force can come? So, I have my adhesive tape, I have my gum, then there are bodies that stick to each other, you have your velcro which binds the bodies together. So, there are many forces. The geckos climb up the walls, for instance, the molecules are bound to each other, the sun and the earth are bound to each other, our whole Milky Way is a single galaxy where the stars are bound to each other. Therefore, there are any number of forces, and a good question to ask is it possible that there is a small number of so called fundamental forces from which everything emerges? There is a question that we can ask, and it turns out that the answer is yes. And with about, let us say, 400 or 500 years of physics, so called modern day physics, we know that all forces can be brought down to one of the four, and that is what I have listed in this slide. The first one is the gravitational force, which binds us to the earth, which binds the moon to the earth, which binds the moon earth system to the sun, etc., etc. The next force is the electromagnetic force, which is operating everywhere. In fact, everything that is happening in our human body is at some sense an electromagnetic force. It binds the atoms, atoms to molecules, molecules to molecules. In some sense, all of chemistry is an approximation to or a applied branch of electrodynamics. Then we know that an atom is made up of an electron and a nuclei. The nuclei are themselves made of protons and neutrons. They are very, very powerful forces because it is very difficult to break an atom. And if you break an atom in an uncontrolled way, actually it becomes a bomb, an atomic bomb. So that enormous energy is contained in the nuclear force. And you people also study beta decay in your radioactivity chapter, probably in your 12th standard. And the interaction responsible for that is the weak interaction. So I have listed all of them. It is a matter of interest to know what the difference between these forces are. So I have listed that in this table. So what I do is I will take the nuclear force strength to be of the order 1. That is what I will take, and I will start comparing all the other forces with respect to them. So gravitation is of great interest to us. You see that gravitation is almost 0 compared to the nuclear force because its magnitude is relative strength is 10 to the power of minus 37. It is an enormously small number. So if we just went by this strength, we should have forgotten all about gravitational force. You should not have any role at all in the dynamics of our universe or in human life. But where gravitation loses in strength, it gains in range. It has an infinite range, and Mother Nature has given us very, very massive objects. And because of that, when you go to very far off distances, gravitation plays a very important role. And that is the reason why you don't worry about the gravitational force, about when I am looking at what is it that holds this pen together. But I do worry about gravitational force when I ask myself, what is it that doesn't allow me to jump away from the earth and escape to outer space? That is what is happening. What about nuclear forces? Nuclear forces are 10 to the power of 37 times stronger, but then their range, their empire is in a very, very minuscule region. So we have the empire of gravitation, which is the whole universe. It is weak, but the whole universe. But the empire of nuclear forces is very strong, but it is in a tiny, tiny region of about 10 to the power of minus 15 meters. Okay? And there it operates, but beyond that it is very difficult to see it. Now comes the electromagnetic force. Electromagnetic forces are only about 100 times weaker than the nuclear forces, and its range is also infinite. So if you people remember, all of you know, even from your 9th and 10th standard, my gravitational force goes like 1 over r squared, inverse square law. My Coulomb also goes like 1 over r squared. So if this is infinite range, my Coulomb force is also of an infinite range. Therefore, a good question again that we should ask ourselves is, why is it that gravitation is able to dominate over electromagnetic forces? Why is it that such a thing is happening? The answer to that comes a very, very peculiar reason, namely, we have mass, which is responsible for gravitational force, and the mass occurs of only one kind. All masses are positive and they all attract each other irrespective of what the mass is. So it is a very happy situation where there is no concept of a repulsion at all. Whereas when it comes to electromagnetic, we know there are two kinds of charges, the positive charges and the negative charges. Like charges, the positive charges repel each other, negative charges repel each other, and positive and negative charges attract each other. And of course, if a body does not have any charge, it does not have electromagnetic interaction. So what we have is, because there are two kinds of charges, If I bring a system of positive charges and negative charges, then what will happen? The system will try to get into a state. In fact, it will get into a state where positive charges and negative charges combine to form neutral objects. Now, the interaction between these neutral objects is very, very small because they are electrically neutral. There will be some small residual interaction because positive charge is distributed in some way, negative charge is distributed in some other way. So, because of that there will be a very, very negligible interaction, and that is the negligible interaction which you study, for example, in van der Waals forces. And that is what changes, for example, your equation of state. In your van der Waals equation of state, you try to put in volume effect, repulsion effect and things like that, and this becomes effectively short-ranged. What is a 1 over r squared force will become a 1 over r to the power of 6 or 1 over r to the power of 7 force. So, this phenomenon is what is called as screening. Every positive charge likes to get surrounded by negative charges. Every negative charge likes to get surrounded by positive charges. The screening takes place, and because of this screening, the effective interaction between objects which are separated by large distances is very weak compared to the gravitational force. So, gravitational force wins. The range of electromagnetic forces is only to the extent of holding objects together. That is what is going to happen. Weak interaction, of course, loses on all counts. It is about 10 to the power of 7 times weaker. That is what I am showing in this particular slide, the last line in this slide. And its range is less than 10 to the power of minus 17 meter. One even wonders why weak interaction is there at all. Well, it has a very important role to play, which you will study probably much, much later in your life. So, that is responsible for weak interactions, and we need not be bothered about that. But by the time you complete your 12th standard, you would have learnt gravitation, electromagnetic, and to a certain extent nuclear forces. When you study fission, fusion, how much energy is liberated in a nuclear reactor, etc., using Einstein's mass energy equivalence. So, this is a good occasion for us to actually record all the forces. So, what I am essentially trying to tell you is that of all these 4 fundamental forces, gravitation is the one which is important for us. The minute the distance between objects become of the order of let us say even a centimeter. Okay? Only when the distance is of the order of a micrometer, electromagnetic interactions become important, and this is what we are going to study. Now, I want to make some very important statements. These things are not there in your textbook, but then if I did not pay attention to that, all of gravitation will appear mysterious. Therefore, it is worthwhile spending some time on this. So, let me start writing down a few things, and please pay attention. Now, all of you know the form of gravitational force. So, let me write in big letters minus G mm by r squared. Okay, let me not bother about the sign at this particular point. So, since I am not being very precise in my mathematics, I will try to be precise with my words, and I will use the word attractive. So, I will also put a G here to remind myself that it is a gravitational force. Now, I told you that applied force is something that I know, and I am going to apply Newton's law to solve this problem. I will look at circular orbits, straight line orbits, rectilinear motion. I will look at the motion of satellites, etc. I will look at escape velocity. You people will solve all those problems. But there is a problem. The problem is, on the right hand side, we have 1, 2, 3, 4 unknowns. As a mathematical problem, it is very easy to solve any problem in gravitation at your level, because you will be asked, a particle of mass m is moving in the field of the sun's gravitational force, and then in your examination, in parenthesis, in brackets, your examiner will say mass of the sun is so many kilos, the distance between the earth and the sun is so many kilometers. and you will also be given the gravitational constant. But now the big question for us is that when you are introducing the concept of gravitation, we have to ask ourselves, how do I determine the so-called universal constant, the gravitational constant, Newton's gravitational constant? How do I measure the mass m? How do I measure this mass m, and how do I measure this distance? This is extraordinarily important. We should remember that the great successes of Newtonian gravitation came from astronomy, and during the time of Newton there was no way of knowing what the mass of the sun is. In fact, it is very difficult even to know what the mass of the earth is. You can only make a crude estimate, and we all know that it is also equally difficult to estimate what the distances are. So what I advise you is, go out and look up at the night sky tonight, and you see, so we have this vision. I think we are able to distinguish separation between objects up to about 7 kilometers or whatever. So that is where you see the sky, and that is where you find the zenith or the horizon, from the zenith to the horizon. Beyond that you can't make out the distance scale. So all the stars, all the planets, everything appears to be at equal distance from us. Well, the moon appears to be bigger than stars, so we don't know whether moon is intrinsically bigger or moon is closer to us. Therefore, we need a number of methods, indirect methods, to be able to estimate the masses and the distances. Let me make this concept a little bit sharper. So how do I make that? Let us start with Newton's equation. So I have a mass, body of mass m, and it is going to move with a certain acceleration, and I want to write g mm by r square. Let us assume that this equation is correct for the time being. Now, one of the curious things that you find, and that is something that I am going to spend quite some time at a later time, is that the acceleration of this is the test mass, because I am only worried about the, so let me write that A has a mass m, B has a mass capital M. So I am going to assume that this capital M is much larger than this small m. So let us say very, very large. I am not going to worry about how the motion of the body A is going to affect the motion of the body B. Now you see, irrespective of what the mass of A is, the two masses cancel each other. Therefore, the acceleration of a test mass in a gravitational field is independent of your own mass. Now that is a real tragedy, because this is the only thing that I can measure. I take a ball and I throw it up, I know the mass of the ball, but that is not going to give me any information. It is not going to tell me anything about the gravitational constant. It is not going to tell me anything about the mass of the earth. It is not going to tell me anything about the radius of the earth. I can write r plus h whole squared, whatever that height is. I only know the height. But it tells me one important thing, that whether you throw a pebble or a block of lead or any other object, so long as frictional forces do not play a role, all of them suffer the same acceleration. And this principle is called the equivalence principle. I will not spend too much time on that, but this is a very, very important principle. I will come to that after I state gravitational law again after a while. But at this stage I want to make the statement, this is called equivalence principle. So the big question is, how do I know capital G, how do I know capital M, and how do I know these large distances? I am speaking of distances like what? The distance between the earth and the moon, the earth and the sun, the moon and the sun, so on and so forth. And this is where the great ingenuity of the astronomers comes in. And we should remember that the groundwork for this great law, Newton's law of gravitation, universal law of gravitation, was laid not over a period of a few hundred years, but over a period of thousands of years. Astronomers all over the world made observations, astronomical observations. They developed the mathematical tools for the understanding these observations, and they came up with great physical insights. Of course, they had to make a number of assumptions. Fortunately, all of which were very, very rational and therefore it was substantiated by observations, later observations in nature. So what I am going to do now is to systematically discuss how these constants can be determined. This is not going to be a very difficult thing because all of you are studying enough mathematics for that. The mathematics at the level of 11th and 12th standard is more than enough for whatever we are going to discuss. So if you now come back to this slide, let me list out what are all the concepts that I am going to discuss. Probably I would have time only for discussing a few of them today. The first that I am going to discuss is the size of the earth. So please look at this slide carefully. I have made 5 bullets. So the first bullet mentions that we should first of all know what the size of the earth is. What do I mean by the size of the earth? I should first of all know that the earth is spherical. I need an evidence for that. Then I should be able to estimate the radius of the earth. Then I should know what the size of the moon is. I should know what the earth moon distance is. Then I should know what the earth sun distance is. In other words, my primary preoccupation first will be in estimating distances. So we are going to take a hierarchical approach. First, get a robust method of getting distances as accurately as possible. Then try to get a robust method of estimating either mass or gravitation together. That is a little bit tricky thing. You need both of them. So let us do that. Historically, what happens is that you should know the distances very precisely. Then you take 2 objects of known masses. You don't have to look at the mass of the moon or the sun or the earth, which is difficult. Known masses, like let's say dumbbell, 2 heavy metal masses. Then use Newtonian law of gravitation to estimate the law of G, the constant of gravitation, the gravitational constant. Then combine that with either the Galilean law of motion or some other law and try to get the mass of the earth, mass of the sun, and then combine with it whatever knowledge of the masses that we are known. So essentially what I am trying to convey you is that studying gravitation, or for that matter any physical force, is not a mathematical exercise. Physics is not applied mathematics. Physics involves very careful observation and a very careful interpretation. And since you are getting exposed to this subject for the first time, this is the time and this is the place for us to actually put in an effort to understand what is happening. So I will start with the concept of the radius of the earth. Now there is a certain fiction which is very popular, namely that people believed that the earth was flat, and there were heroic people sometime in 15th century, 16th century, 17th century who believed that the earth was actually spherical in shape, and they were great heroes, they were willing to give up their life. So we have the lore of Columbus, who decided to reach India by travelling westwards instead of travelling eastwards. But these are really essentially fiction. They may be inspiring, but they are not correct, because astronomers all over the world over more than 1000 years knew that the earth is a spherical object and so is the moon. And the evidence for that came from eclipses. So there is a certain mythological literature in every civilization, whether it is Sumerian or Babylonian or Greek or Roman or Indian or Chinese, where you say, the earth is flat, the earth is supported by so many elephants, or in the Greek mythology, I think it is Atlas or somebody who holds the earth. So you could be anybody, okay. We should not confuse that these mythological stories, they have their own very, very important role to play, because it speaks of the human psyche, not about the nature of the external world. But astronomers always knew that earth is spherical. So to give you an example from our own country, for example, the great astronomer, mathematician Aryabhatta, he lived in the 5th century AD, not too early. He argued that the earth is spherical in shape, and when the student asks him, if the earth is spherical in shape, why is it that I don't fall off when I am on the other side? Aryabhatta correctly answers and tells him, look here, when I look at earth as a sphere, there is nothing called up and down which is absolute. Up is when you move away from the surface of the earth, and down when you move towards the earth. So in a similar manner, if I am coming to the diametrically opposite point, okay, when I am standing here, I may say I am going down under the earth. That is what we say, down under. But once I come here, up is away from the surface of the earth, down is towards the earth. In fact, Aryabhatta also argues that there is a mysterious force that holds everything together. Of course, at that time they did not know anything about gravitational force. So he says that it is in the very nature of the things. So astronomers knew that. We are not saying that Aryabhatta was the first person to make such a statement. The Greek astronomers, or probably even other astronomers in Egypt or Babylonia, these people knew that essentially all heavenly bodies, including the earth, were all spherical in nature, and they were all in space. They were all moving. As to who was moving with respect to who is a different question altogether. For example, the Indian Astronomical School seriously believed that there are very, very powerful winds which direct the heavenly bodies to move in prescribed orbits. So that was their model for the force. There can be sophisticated versions of that, but the point is that I want to be able to determine the radius of the earth. There are many, many crude ways of determining the radius of the earth. So you might study this. If the earth is a spherical object, you give a certain height and you ask how far I can see. So this is my radius, let us say. This is an exaggerated figure. So I will make use of trigonometry. As the height keeps on increasing, I can see farther and farther. I know this height, I know the angle, I know this distance. Therefore, from that I should be able to estimate the radius of the earth. So this is rather crude. In fact, the simplest version that I can state is that I am a person, let us say, okay, let us take a person who is about 6 feet, 6 plus something feet tall, about 2 meters, let us say. So there is a person 2 meters tall. How far can the person see? Because of the spherical nature of the earth, because the earth is going to get curved. If the earth were flat, your range of vision would be infinite. You would be able to see beyond infinity. Of course, you don't see buildings or human beings, or for that matter, the tallest buildings which exist in Dubai or whatever place, we are not able to see them because of the sphericity. So go home, make a simple model and estimate what the radius of the earth is. So this is something that we can do. So this is a simple example. These things do not prove that the earth is spherical. You will have to do a navigation, which is what people did, and people knew fairly lot. For example, Ptolemy's book on geography contains a large number of sites in India, both along the western coast and the eastern coast. So people sort of fairly knew that earth is spherical in nature. What I want to show for you is an extraordinarily beautiful estimate of the radius of the earth by Eratosthenes. Eratosthenes lived in the 4th century BC. So please look at this slide. I hope this is visible to all of you. Otherwise, anyway, I will write on the sheet of paper and I will show it to you. Eratosthenes was indeed a great mathematician, and he was not an armchair mathematician. He was a person who also did observations by traveling long distances, and he lived in the 4th century BC. Okay? So I was speaking of Aryabhatta in the 4th century AD. So we are now speaking of the 4th century BC. So we are speaking of a span of 800 years. 800 years before Aryabhatta made his statements, Eratosthenes already had found good methods of estimating the radius of the earth. So let me explain that to you. So what you have is the surface of the earth, and what you have to do is to pick up a particular day. In fact, for us, a good particular day should be something like summer solstice or the winter solstice. He probably did not do that because on that particular day the sunlight falls directly either on Tropic of Cancer or Tropic of Capricorn, 23.5 degrees either north or the south, never mind about that. But the whole idea is that there were 2 points, so that is what I have to worry about. This point corresponds to Alexandria and this point corresponds to Aswan. In fact, this was a well. This was a well in Aswan and well contains water. So that is what we have. Now the distance between them is known and that was given to be, I am reading straight away in this, 50 stadia. So this distance is 50 stadia. So the unit of distance is a stadium. Stadium is a place where we go and sit in order to watch. In India, a distance was called, a unit of distance when people travel was called yojana. In Greek, it was called as stadium. The only problem with the concept of stadium or yojana is they keep on changing with time. The measures keep on changing with time, but the name persists. So we have to be a little bit careful. Now the point is, I know the distance between them. We will convert this stadia into ordinary units in a while. Now I am going to draw another picture because I have already used it up. So this is one point, this is another point. On that particular day, this is a highly exaggerated figure. There is a well here. The sun's rays were falling perfectly normally. It was making 90 degrees. Now obviously, if I am going to look at this point, it should be sufficiently far away, it makes a certain angle. That is why the length of the day and the length of the night keeps changing, correct? So if you go to the poles, you have 6 months of day and 6 months of night because of that particular reason, because the sun's rays become more and more tangential and after a point they stop reaching that. In this particular, for example, region, that is what you have. And we should know what the angle is, and this angle is about 7 degrees. This angle is about 7 degrees. And now I am going to extrapolate this. So let us say that this is my center of the earth. So this is what I have and this is what I have, and this is 90 degrees and this is 7 degrees and this is my radius of the earth. So what should I do? All of you have studied the formula S equal to r theta. When I speak of the distance, I do not mean boring a tunnel and finding out what the distance between these 2 points is. It is the distance travelled by these 2 points when I move on the surface of the earth. So I am really looking at, yes, it is the total distance covered, not the Euclidean distance, okay, not the shortest distance. Now you know theta, because this was 7 degrees, you know what this angle is. I will leave that as an exercise for you people. So your r is essentially given by S by theta. S is a fairly small quantity, namely 50 stadia I told you, but theta is very, very small because 7 degrees is very, very small and theta should be written in units of radians. So 2 pi radians, you have to divide it by whatever the 2 pi is. If you work out, you should be able to estimate the radius. At this point, I should point out to you people that Eratosthenes was either a lucky person or a very smart person, because this argument works out only if both of them are at the same longitude by hindsight. If you move away to some other longitude, then you cannot estimate that, but it turns out they are roughly at the same longitude. Go to the globe and look at that, and Eratosthenes was able to get that. Okay. Now it was not 50 stadia, I am very sorry, it was 5000 stadia. The distance was 5000 stadia and it translates to 800 kilometers. Yes, translates to 800 kilometers. Now if you plug in and if you try to find out what the radius is, you get Did you get the radius or the circumference? He estimated the circumference, multiplied it by 2 pi r, you get 40,000 kilometers. So, circumference is equal to 2 pi r is equal to 40,000 kilometers is what you are going to get. I think the current radius of the earth, I forgot to write that down, is about 6400 kilometers. So, take 6400 kilometers multiplied by 2 pi whatever. So, that is 6. 6 into 6 is 36, and there is another 4 into 6, 24, 38,400, and there are some corrections because I simply used pi is equal to 6, it is 6 point something, and therefore you see it is remarkably very, very close to the current value. So, what we are able to do is to make use of known trigonometry, whatever you study by drawing triangles and circles. Okay? In fact, all of trigonometry was developed in order to understand the heavenly motion, okay, and make, of course, trigonometry was also required for sculpture, for architecture, for buildings, for demarcating areas, so on and so forth. But it was also used primarily and developed primarily for astronomy, and this is one of the great achievements of human ingenuity. You may wonder how he measured this to be 5,000 stadia. Actually, it is a very interesting thing. He knew the circumference of his wheel, and he tried a small stick, and he actually sat on a cart. Let us call it a chariot. So, this chariot is being driven by a horse, and every time the wheel of the chariot completes one circle, that stick hits the ground. So, what does he do? He keeps on counting the number of times the stick hits the ground. So, you know how many circles, how many revolutions the wheel has completed, and you know the circumference of the wheel is 2 pi into the radius of the wheel multiplied by the total number, and that gives you the total distance that is covered. So, this is how people actually devised simple, effective and ingenious methods in order to measure large things. And these are the things that we should imbibe. It is not necessarily solving a problem in a smart way. It is not a question of, I integrate by substitution or by integration by parts. These are not the only skills. Those technical skills are also required. So, this is done, and we have a fairly good idea of what the radius of the earth is. Actually, if you give me the radius of the earth, it should not be too difficult to estimate the mass of the earth also. If I know what should be the mean density, but that is a different story altogether. However, at this point we should remember that this involves a large number of assumptions, namely, in fact, when I look at other situations, it will involve even larger number of assumptions, and that is, whatever law of mathematics, whatever results in mathematics I have obtained from my daily observation, they are also valid at large distances. So, let me make that statement. So, I draw a triangle and I measure the sum of the angles of a triangle to be 180 degrees. Now, that of course is a theorem, because I am saying that two parallel lines won't meet each other. That is an axiom, correct? That is what I am assuming. In other words, when I am using these quote unquote mathematical results for deriving conclusions from physics, how do I know that these results are correct? I know them because I found by observation. It does not help a physicist to say, oh no, they are absolute results because they are mathematical results. Unfortunately, that is not correct, because the so-called axioms of mathematics have to be verified by observation. There is no reason why two parallel lines should not meet. There is no reason why Pythagoras theorem should hold. They are all equivalent to each other. There is no reason why the sum of three angles of a triangle must be 180. Maybe it is greater than 180, maybe it is less than 180. This is something to be verified. But then this realization came much later, only sometime in the 17th or the 18th century, not even during the time of Newton. People assumed that there can be no other properties of nature that are possible other than what Euclid wrote in his geometry, for example. That was the universal assumption. And it turns out, when we are measuring distances between the earth and the sun, the Earth and the Moon, and even the nearby stars, these results are robust. But if you go to far, far distances, those results are not robust. There are going to be corrections. So the message that I am trying to tell you is that physics is different from mathematics in the sense that the so-called fundamental axioms of mathematics are themselves under constant verification in physical laws. We have to know what the correct mathematical principles are that we should use. For example, we say Romer measured the speed of light by looking at the eclipses of moons of Jupiter. You know the distance, you know the time taken. Actually, there is a very, very major assumption that we make, namely light travels with constant speed between its emission and reaching the Earth. That is an assumption. So the way physics works is that you make an assumption, you make a hypothesis, you verify, you get a conclusion, and then you make further predictions, so on and so forth, and you make a correction. So please remember, throughout your course, whatever you are doing in 11th, 12th and beyond, we are going to take the viewpoint that physics is not applied mathematics. Laws of nature are not God given, although we call it universal and all that. It is our modeling, and everything requires very, very strenuous and a diligent verification to better and better accuracy. That is something that we have to do, whether it is electromagnetic theory or gravitation or strong or weak. This is the spirit that we are going to take in order to continue our studies. So let me come back to the slides. So please go back and work out the great result of Eratosthenes. It's a great thing. Now what I want to do is to estimate the distance between the Moon and the Earth. I am not going to work out all the details because the fun of it will be taken away. As I told you, people knew that the Moon itself should be a spherical object because we have the phases of the Moon. And the phases of the Moon are there because a part of the spherical surface gets reflected, whatever is, and the other part is in the shadow region. So we also know that we get the new Moon when the Moon is completely on the opposite side of the Earth. So what are we saying? To put it very crudely, you have the Sun, you have the Earth here. So the full moon the new moon is when the Moon is here. This is the Sun, this is the Earth, and the full moon is when the Moon is here, because that is what we have. In fact, the orbit of the Moon is slightly inclined to this plane, otherwise every full moon we would have had an eclipse. There is no escaping that, we would have had an eclipse because the Moon would come between the Earth and the Sun. There would have been a solar eclipse, but such a thing does not happen anyway. So now what we can do is ask what happens at a half moon. Half moon is the 8th day, what we call as the Ashtami, right? Now the Moon is a perfect semicircle. So we have the full circle on the full moon night, absolutely no circle because there is a complete shadow on the new moon. So now you look at what happens when there is a half moon, therefore the Moon should be here obviously. So this part of the Moon, let me exaggerate that, this part of the Moon is getting illuminated, so I see this, the other Moon is not getting illuminated, therefore I only see half of it or whatever, the Sun's rays is coming. Now this estimate was done by Hipparchus. So Hipparchus said that this should be 90 degrees here and this is what I have. So all that I need to know is this angle. If I know this angle very precisely, I should be able to estimate the Moon-Earth distance. Is that okay? Or at least the ratio. Again, I am not going to work this out because it will take us far, far away, except that the very concept of a half moon is a very tricky thing. How do we know it is exactly a half moon? And you know, the whole thing is that in all these situations, remember, we are using a formula like S equal to R theta. We are going to approximate sin theta by theta, and very small errors in theta will give rise to very large errors in estimate of the distance. We should be careful about that. But this was done, and you can get a fairly good estimate between the distance between the Earth and the Moon. So, we have to worry about the earth and the star distances. So, probably what I should do at this particular time is to actually stop, because maybe instead of leaving these examples to you people, in the next lecture I will myself work out how you get the angles on the half moon day, and then I will introduce the concept of a parallax, which is extraordinarily important, and they will show how the distance between the earth and the stars can also be measured. In fact, measurement of parallax also brings into the fore a very, very important question, and that is a question which plagued all the ancient astronomers, and that is whether the sun goes around the earth or the earth goes around the sun with respect to the background stars, and we will take that in the next class. So, if you find time, please read them up and come, so that you will be well prepared. So, let us stop now. Have a good day.